Welcome back, everyone. I know this is like getting very odd to have class at this time of the year. Your exam is going to be held in January. So I think I will just take today's class because I have already started partial differential equations. So I thought I would quickly finish partial differential equations, and then uh, after that we have one or two lectures remaining, so that we can do it, I think, in January before your exam, so that I think everybody will be in a better mood to have class, because for the past few weeks I was busy with undergraduate examinations and syllabus preparation and all. But now that I'm free, but I think it's a little bit odd, very odd timing to have a class. So anyway, in I will just need two or three lectures, probably three lectures to finish the syllabus. After today's class, we will continue in January only. So I don't feel like requesting you or calling you for a class at this time of the year, when the winter session, winter vacation already sets in for most other classes. Okay, so we'll just take two or three classes in January after today's. In our previous class, we have talked about different types of partial differential equations. Different types of partial differential equations. Some of them we call it elliptical, parabolic, and hyperbolic partial differential equations, right? So we have classified it as elliptical, parabolic, and hyperbolic. Also, partly the reason why I could not continue my class was that my pen that I used for writing on the laptop screen, the battery ran out. I look for the battery in ISO. I search for not AAA, it's a 4A battery. It's a very small battery. I look for many shops, even including computer gadgets shops and other things, and I could not find 4A battery in ISO. And then I look for a new stylus pen with which a battery will be provided, but stylus pen is also very rare in Mizoram. So in my laptop, particularly in this touchscreen laptop, we cannot use the normal stylus pen that are normally used in your mobile phone, and what is that? Some other notepad and all. So those kind of stylus pen which does not need battery, they are not suitable, they are not compatible with my laptop. So I have to look for one particular type of stylus pen which has its own battery source within it. So without my pen, I cannot, it was not convenient to take class. So eventually I ordered it from Amazon. So it arrived, I think last Saturday it arrived. But since then, yeah, I think it was Monday it arrived. Yeah, now only I can continue the class. Right. So we discuss about these types of elliptical, parabolic, and hyperbolic, these things, and we classify it according to b square minus 4ac, whether it's greater than 0 or equal to 0 or less than 0. So depending on that, there was a classification that we discussed, and you can just quickly see my lecture video once again. Now, in today's lecture, we are going to study a method for solving this kind of partial differential equations, particularly elliptical and parabolic. Hyperbolic is not needed. So hyperbolic, if I have time, I will just provide you also, but more or less same as parabolic. So we will study numerical techniques for numerical techniques for solving partial differential equations. Right. So numerical techniques means a technique which can be implemented or incorporated in computer programming technique which we can incorporate in computer programming. And one of the technique and most commonly used is called finite difference approach. Okay. Finite difference approach. So this finite difference approach or finite difference method of solving partial differential equations is what we are going to study today. Now, we all know that, like, for example, let us consider one of the most common partial differential equations, like which you encounter in many situations. Most common partial differential equations. One of the most common ones is called what is that? Laplace's equation. Laplace's equation. What is a Laplace's equation? Laplace's equation is simply del square v or u or whatever potential you are using equal to 0. Okay. So here u or v, whatever it is, it describes the potential in a certain region of space. So if we are considering two-dimensional space, let's say this is x, let's say this is y, you are considering two-dimensional space, u is a potential field. U is a potential field that is a function of x and y. U is a potential field or a scalar field which defines the potential, the electrostatic potential within this region of space. Right. So at any point, at any coordinates value, at x and y, at a certain x, y values, let's say x value is 3, y value is 2. So at this point, x equal to 3, y equal to 2, this U will define the electrostatic potential at this point. So any point within this space, region of space, the electrostatic potential can be expressed using this UXY. And the equation governing the electrostatic potential in this region of space is what is known as Laplace's equation. So in this region of space, if there are no free charges, enclosed within this region of space, if there are no free charges enclosed within this region of space, then the equation that defines or that governs the electrostatic potential in such region of space is what we know it as a Laplace's equation, del square U equal to 0. Now, how you usually solve this kind of problem is that your analytical approach, analytical approach using your pen and paper, you can easily solve it. Easily, not so easily, in depending on the certain situations. So it's a 2D means del square operator will be del square upon del x square plus del square upon del y square u. Right. So u as a function of x and y, you can use what is called separation of variables. That is a function which is purely a function of x, a function which is purely a function of y. So you can use a separation of variables. Using this separation of variables, you can write this as y d square x upon dx square plus x d square y upon dy square equal to 0. And if you divide both sides with xy, then this will be 1 upon x d square x upon dx square equals to minus of 1 upon y d square y upon dy square. And you can equal these two terms in which is entirely consisting of x and a function of x and y variable and a function of y, they are equal, means they are probably equal to certain constants, let's say kappa. So now separately you can solve differential equations consisting of x only, and differential equation consisting of y only, minus of 1 upon y d square y upon dy square equal to k. So separately you can solve, and then after solving or after finding x as a function of x and y as a function of y from solving this differential equation, and from solving this differential equation, then you can get your functional form uxy. So once you have the functional form uxy, let's say the functional form uxy is 3x squared y plus y cube, something like that. So if uxy, the functional, once you have the functional form of your u, once the functional form of u is known to you, by putting x and y coordinates value, you can know what the value of your u will be at a certain point. Let's say this point is 3, 2 coordinates. So you put the value of x as 3 here, y as 2 here, then you will be able to determine the potential, the electrostatic potential value at this point, right? So solving this partial differential equation means our intention eventually is to find the functional value u, the value of u at every point within this region of space. So in this analytical approach, we use separation of variable approach, and after using separation of variables, we obtain the functional form of uxy. Once we have the functional form of uxy, then we put the value of coordinates variables like x and y values, then you get the value of your u. You get the value of your u at any point within the space. So eventually solving means to determine or to know the value of your variable u at every point in the space, right? That is our objective. Now this kind of analytical calculation, like writing this separation of variables and all these things, you cannot do it in a computer, right? You cannot put in a computer programming. So in order to be able to use very powerful computing tools like our machine, we need to study, or somebody has developed this finite difference approach, and that is what we are going to study, right? So in finite difference approach, what we are doing is, let's say we have a certain region of space, whatever maybe it, whether it's a rectangular or a sphere or spherical, circular or anything, whatever may be. Let's say for simplicity, let us consider only 2D system. Okay, simplicity, let us consider only 2D system. Let's say this is your x-axis, let's say this is your y-axis, and of course you can consider 3D system also, but for simplicity let us consider only a 2D system for now. 2D system. Now what we do in the finite difference approach is that we transform this region of space, into in finitesimally small elements. So we kind of we sort of divide this region of space into a large number of cells. Okay, a large number of cells, small, infinitesimally small cells. So this is what we do in a finite difference approach. We just divide into this some kind of discrete cells. Okay, some kind of discrete cells. So we just divide it into them, and we define our u. Let's say this is your x-axis, let's say this is your y-axis. So we define what is called numerically like discrete value of u, uij. I stands for the x indices, I for the x direction, j is the index for the y direction. So let's say we define this quantity as uij. Okay, uij. Now if you move one cell along the positive x-axis, the next cell will be ui plus 1j. Okay, oops. Yeah, I hope you can read it. Ui plus 1j. And if you move backwards towards negative x-axis, the next cell over here is called ui minus 1j. Now, if you move up along the y direction, the cell above is called ui j plus 1 cell. And the cell just below this uij is called uij minus 1 cell. So likewise, this would be j minus 2, j minus 3, j minus 4, like that. Okay. So if the step size along x-axis is taken as h, and step size along y-axis is taken as k. Okay. Now, in this finite difference approach, we are going to define a certain terms like central difference and all. Okay. Now, let's say along x-axis. Let us consider along x-axis. So you see that this cell is your uij cell. You have uij cell, and adjacent to that, if you move to the next cell, then this is called your ui plus 1j cell. If you move in this direction, the next cell is called your ui minus 1j, and the step size here between this is called your h, step size along the x-axis. This is how we define it along the x-axis. Right. Now, let me define what is called the central difference. So in the central difference approach, del u by del x, that is differentiation of u with respect to x, can be expressed as u I plus 1 j minus u I minus 1 j upon 2h. And there is this thing called forward difference. So in forward difference, derivative of u with respect to x is defined as, say, forward difference means the one on the front side. This is your central position. The one on the front side, on the front side or the forward side of along the x-axis, along the positive x-axis is ui plus 1j. The one on the back side or the reverse side of this x-axis is u minus 1j, right? So in central difference, we just take the difference between u I plus 1j minus ui minus 1j, and the interval here is 2h. H plus h is 2h, right? So in the forward difference, we are going to take between these two. So this is called forward difference. And in the reverse backward difference, we are going to take between these two. Okay. The backward side or the reverse side, that is the back side, u minus 1j and uij. That's what the approach is. So in a forward difference, we just define the partial derivative of u with respect to x as u I plus 1 j minus u I j upon h, and we define what is known as backward difference. So in backward difference, del u upon del x is taken as u I j minus u I minus 1 j upon h. Okay, that's how we define, like once we divide this region of space into this kind of mesh, this kind of cells, infinitesimally small cells, then we can define the derivative of u with respect to x in that process, in that way. Right. Now, if I take if I have what is called second order derivative like this, the second order derivative del square u upon del x square is simply defined as del u upon del x forward difference minus del u upon del x backward difference upon h. Okay, this is how we define the second order derivative along x. Now let us consider along the y-axis. Okay, along the y-axis, let's say we have our original cell as uij, and the next cell above this uij is uij is the index for the y-axis, uij plus 1. And the step size or the interval here is your k. Now the next cell below this will be uij minus 1, and the step here size here, the interval here is k, right? Uij minus 1. Just wait, somebody is coming. So I'm just here alone in the department. So I thought somebody was knocking at the door. Anyway, all right. So like I explained here, uij, and the cell just above this is uij plus 1. The cell just below this is uij minus 1. So like that, the step size here is k. So let us define a similar term called central difference. So central difference approach is that we just take the like the upper one, and that is the forward one, and the backward one, the backward cells, and the interval is 2k here in this case, 2k. So like this we can write uij plus 1 minus uij minus 1 divided by 2k. And forward difference, so once we define the region of space into discrete cells, using this numerical approach, using these discrete cells, we can now define the partial derivative. So the forward difference approach will be uij plus 1 minus uij upon k. Backward difference will be del u upon del x. This is how we can define uij minus uij minus 1 upon k. Okay, so similar to this. And we can also define, oh sorry, this is along y axis. We are talking along y axis, right? Y axis, so it has to be del u upon del y, partial derivative with respect to y, del u upon del y. So sorry. So del square u upon del y square can be written as del u upon del y forward difference minus del u upon del y backward difference divided by k. Okay, that's how we can write the second order derivative. Now if you consider what is called like the cells like this, uij, let's say this is the middle cell, and the cell just adjacent to this is ui plus 1j, and on the back side this will be ui minus 1j, and on the top side this will be your ui j plus 1, ui j minus 1. So using this, once you discretize the space, you can write your 2D Laplace's equation like this. 2D Laplace's equation. What is that? Your 2D Laplace's equation is del square u upon del x square plus del square u upon del y square equal to 0. And you can write this as what is that? Your del square u upon del x square. Somebody is calling. Oh, hello, pa. Masa ka karon tirong kaman che lo ke mai mo masa kan belok ngo creative han karon tlan so tirang. Le kan bing lo hang mai ro masa mun dang ko su just 1 minute, guys. So don't worry about the time limit here because I use a licensed version. We can have the class as long as we like. It's just one family. Yes. Oh, hello, miss. Kapa ka ho du to mo kon phui lok mai te lo phone la khida bazar bum kon chen ma dewa ka creative building ki frame aizol watch house chen ma dewa aizol watch house building ki frame ro ka mi chen ma dewa creative building ka creative ko va ko ma sangai na zo din la ko ma sangai lo heta treasury kilometer kalanga tro zodin square ai tan phe ta tro zodin square ai tan phe ta hotel rich shre tro hotel rich pe shre da khan creative ti om kha velama ai zo watch house thlen ma khan creative form ka va kol ma saloin kong sira khan lo amang phone ro ka pa phone ro to na okay. So del square u upon del x square. So this is a very simple approach. Like this will be del u upon del x, what difference, minus del u upon del x, backward difference upon h, and del square upon del u square will be, you know that this forward difference is u I plus 1 j minus uij upon h minus u backward difference is ij minus u I minus 1 j upon h and divided by h. So if you simplify this further, this you can write as del square u upon del x square as del square u upon del x square as just a minute. Yeah, ui plus 1j minus into minus is plus ui minus 1j minus 2uij. Okay. So this will be ui plus 1j minus 2uij plus ui minus 1j divided by here h is a common factor. There will be an h square now, h square. So using this you can write it, the partial differentiation or the second order derivative of u with respect to x like this. And along y-axis you can also write this as del square u upon del y square as del u upon del x forward difference minus del u upon del u upon del y backward difference minus divided by k is the step size, and this will be ui forward difference means j plus 1 minus uij divided by k minus uij minus uij minus 1 divided by k. So you can, if you simplify this will be ui j plus 1 minus 2 uij plus ui j minus 1 divided by k square. So you can write it like this. Now your partial differential equation del square u upon del x square plus del square u upon del y square equal to 0. It will be simply written like this. Del square u upon del x square will be u I plus 1j minus 2 uij plus ui minus 1j divided by h square plus ui I comma j plus 1 minus 2 ui comma j plus ui comma j minus 1 divided by k square equals to 0. Okay, now if you choose same step size, that is h is equal to k, h is equal to k, same step size, h is equal to k. So my handwriting is not that good. If you do that, this h and k, if they are equal, if you transfer to the right hand side, they will be multiplied with 0, so it will be 0. Now eventually what we going to have here is that here u I plus 1j plus u I minus 1j plus u I j plus 1 plus u I comma j minus 1 minus 2 uij minus 2 uij. If you add, this will be 4 uij equal to 0. Uij equal to 0, right? Sorry, minus 2 uij minus 2 uij, that means minus 4 uij. So you can express uij like this: ui comma j as 1 upon 4 ui plus 1j plus ui minus 1j plus ui j plus 1 plus ui j minus 1. Okay, so this is the formula that we are going to use it for finding your uij values. Now let us try to solve one problem. That is, let me write the question here. Solve del square u upon del x square plus del square u upon del y square equal to 0 for boundary values as shown in figure. So let's say we have a certain boundary problem like this. So let's say we have a certain boundary problem like this. Let's say this is your u1. Let's say this is your u2. Let's say this is your u3. Let's say this is your u4, and let me define our problem something like this. So if we can discretize our problem, electrostatic problem, something like this. So the boundary on this side is, this corner is 1, this value is 1, 2, 3. At this boundary the values are defined like this. Let's say 5, 5, 5. At this boundary the value is, let's say 4, 3, and at this point, let's say the boundary value is 2. This point the boundary value is 1. So let us look into this problem. Okay, so a very simple approach for solving this boundary problem is using this formula. Our finite difference formula is here. So the solution will be like this. For u1, to find the value of u1, you can write like this. u1 will be this particular cell. So in this case, 1 upon 4. So if you are looking at u1 here, what will be ui plus 1j? Ui plus 1j will be along the x-axis, isn't it? This is your x-axis, this is along the y-axis. For u1, say we know that using this finite difference approach that we have just explained, this Laplace's equation can be, see, this is our Laplace equation. So this Laplace's equation, using this finite difference approach, we can rewrite it like this, we can rewrite it like this, and eventually the Laplace's equation is rewritten like this. So this relation uij equal to 1 upon 4, this is what we arrive from the Laplace's equation. So if we consider this Laplace's equation, that means our uij will be expressed like this. All right. So u1. So for considering u1, that is, consider that your uij is u1, and this u2 will be your ui plus 1j, and 1 on the left side will be ui minus 1j, and 1 at the upper side of this will be uij plus 1, and this u3 will be your uij minus 1, right? Uij minus 1. So considering that ui plus 1j will be your u2, so let me put it as your u2 plus ui minus 1j. If you consider this as uij, ui minus 1j will be 1 here, plus uij plus 1, uij plus 1 will be 1 here, uij minus 1, j minus 1 along the y-axis, the cell just below this will be your u3. Okay, so you have u1 like this. And similar to that, you can write for your u2 using your finite difference formula. u2 will be 1 upon 4, 1 upon 4 again. So if considering this u2, for this, consider this as your uij. I plus 1j will be 4. So this will be 4 plus, and your ui minus 1j, if you take this as uij, ui minus 1j will be your u1. So this will be your u1 plus uij plus 1. This cell just above this u2 is 2, right? So this will be uij plus 1 will be 2 plus your uij minus 1, cell just below this will be your u4. So this will be your u4, right? And for, you can express u3 as like using this finite difference formula 1 upon 4. So if you take this u3 as your uij cell, then I plus 1j will be u4 here. So I'll just quickly do it, u4. I hope you get my point now. I minus 1j will be your 2 here, and ij plus 1 will be your u1 plus ij minus 1 would be 4 here, and your u4, if you consider this u4 cell here, will be I plus 1j is 5. Oops. 5 plus I minus 1j is u3. j plus 1 is u2. J minus 1 will be a cell just below this u4 will be 5. The boundary value is 5. Okay, so we have a set of what is that, 4 sets of 1, 2, 3, 4 linear equations for this u1, u2, u3, and u4. Now I think you have already covered what is called Gauss-Seidel method. Gauss-Seidel method. So we can use a Gauss-Seidel method for solving this kind of set of algebraic equations. Gauss-Seidel method. You have already studied this method with Sardibia. So the Gauss-Seidel method approach for solving this kind of set of algebraic equations is that we take what is called, for the first iteration, iteration number 1, we take the initial values. We just assume or take the initial values as u1 equal to 0, u1 equal to u2 equal to u3 equal to u4 equal to 0. So we just started with this, and here in this, for solving u1, we will just put u2 and u3 as 0. Okay, u1 will be 1 upon 4. Your u2 is 0, your u3 is 0, so there is a 1 plus 1, 2. Okay, 0 plus 1 plus 1 plus 0. This is 1 upon 4 into 2. This will be 0.5. And for u2 calculation, we will take the latest value of u1. The latest value of u1 is 0.5, and the latest value of u4 is 0, right? So 1 upon 4, 4 plus u1, the latest value is 0.5 plus this is 2 plus u4, the latest value of u4 is 0, so we just put this. So 4 plus 2 is 6, 6.5. 6.5 divided 4 plus 2 is 6. 6.5 divided by 4 will be 1.625. Okay, now we can solve your u3 as 1 upon 4. So u3 is u4, the latest value of u4 is 0 plus 2 plus u1. 2 plus u1 is 0.5 plus 4. So here also this would be 1.625, and you can write your u4 as what is your u4 now? Here u4 is 1 upon 4, 5 plus u3 plus u2 plus 5. So 1 upon 4, 5 plus u3 plus u2 plus 5, right? 1.625 plus 1.625 plus what is that? Yeah, 5 here. So like this, you can find the value of your u4. Your u4 value is 3. If you calculate this using your calculator, 3.3125, something like this. All right, now you can go for a next iteration. Iteration number 2. Iteration number 2 will be to find the value of u1 again. The value of u1 is from the formula 1 upon 4. Remember, u1 is 1 upon 4, u2 plus 1 plus 1 plus u3, right? So your u4 will be, u2 is 1.625 plus 1 plus 1 plus 1.625. So if you calculate this using your calculator, you will get 1.3125. Okay, and you can calculate your u2 using the same formula. The formula for u2 is 1 upon 4, 4 plus u1 plus 2 plus u4, u1 plus 2 plus u4, right? So here 4 plus u1 value, the latest value is 1.3125 plus 2 plus, what is that? 4 plus u1 plus 2 plus u4. 4 plus u1 plus 2 plus u4. Our u4 latest value is 3.3125. In the next iteration, we always consider the latest value. Then this will come out to be 2.6562. And you can calculate your u3. u3 will be 1 upon 4. Again, use this formula for calculation of u3. Okay, use this formula for calculations of U3, but put the value of the latest value of U4 and U1. So if we do that, this will be 3.3125 plus 2 plus 1.3125 plus 4 equals to 2.6562. Now you can calculate your U4 from what is that? Yeah, U4 from this formula. So put the latest value of U3 and U2 and use this formula for calculating U4. So this will be, yeah, U4 3. Oh, why did I write U4 here? I can continue U4 here. Sorry. U4 will be 1 upon 4. 5 plus 2.6562 plus 2.6562 plus 5. So use calculator to obtain this value. This will be 3.8281. Okay. So once we calculate the subsequent iterations, you can calculate the relative error like this. Relative errors. The relative error formula is that error will be absolute value of U new minus U old divided by U new. So we will use this relative error formula. So now the relative error for U1 will be like this. Let me write U1 our relative error U1 relative error. This will be okay. So what was the latest value in iteration number 2? U1 is 1.3125. 1.3125 minus the old U1. So in iteration number 1, U1 was 0.5. 0.5 divided by U new, that is 1.3125. So you can calculate this using your calculator. You will find this as 0.6190. Like this, we can calculate for the relative error for U2. The relative error for U2 will be like this. What was in the second iteration? What was U2 value? That is 2.6562. 2.6562 minus in the first iteration U2 value was 1.625. 1.625 divided by 2.6562, and if you calculate the relative error here in this case, I think we have to use a calculator, otherwise I don't know. Just 1 minute. So this will be 2.6562 minus 1.625 divided by 2.6562. This will be 0.3882, and you can calculate relative error for U3 as what was the new value of U3 from the second iteration. This is 2.6562, 2.6562, and U3 in the first iteration was 1.625. 1.625. Okay, and divide by 2.6562. Yeah, this you will get the same error, 0.3882. You calculate the relative error for U4. Relative error for U4 means the latest value of U4 is 3.8281. 3.8281 minus the latest the old value of U4 from the first iteration was 3.3125. So 3.3125 divided by 3.8281. This you will obtain your relative error as 0.1347. Okay. So like this, we can form a kind of table, something like this. Let me draw a table like this, then you will realize what it is. So the technique is quite simple, but the calculation process is a little bit tedious because it's a numerical approach. If you do it in your pen and paper, it takes time, but for computer, this kind of numerical calculation, it executes very easily. So let me try this as a maximum error here. Now this is iteration. Just a minute. I have to move this control. Iteration number. Let's say this is your U1, U2, U3, U4. In iteration number 1, like here. In iteration number 1, U1 was 0.5, U2 was 1.625, 1.625, U4 was 3.3125. Okay. So we put that. Iteration number 1, U1 was 0.5, 1.6250, 1.6250, 3.3125. And if we look at iteration number 2, U1 was iteration number 2, U1 was 1.3125, 1.3125. U2 is 2.6562, same as U3, 2.6562, 2.6562. Your U4 is 3.8281. 3.8281. Now here, in these consecutive iterations, you calculate the error in U1, U2, U3, U4, right? So the maximum error, see, if you look at this, the error in U4 is 0.1347 only. The error in U4 is 0.3882. The error in U2 is 0.3882. The error in U1 is maximum or largest, that is 0.6190. Okay, so out of all this error in U1, U2, and U3 and U4, the largest error is obtained for U1. So in the calculation of U1, you have maximum error, that is 0.6190. Okay, so you have to write 0.6190 like that, right? So if you continue the third iteration, you have to continue the iterations like this. So for a third iteration, let me write iteration number 3. Iteration number 3. In iteration number 3, you calculate your U1 again. U1 formula was 1 upon 4. What was that? I have to check once again. 1 upon 4 U2 plus 1 plus U3, right? U2 plus 1 plus U3. So now what was U2? 2.6562. Okay, 2.6562 plus 1 plus 1 plus 2.6562. So you have to calculate this. Obtain the value of U1, and then you can calculate your U2, U3. You calculate U2, U3. You calculate U4 and find the relative error for U1, relative error for U2, relative error for U3, relative error for U4. Okay, and then after that you put whatever values you obtained here in these tables, then go for the next iterations, iteration number 4, iteration number 5, iteration number 6, iteration number 7, iteration number 8, and eventually when you perform the iteration number 8, the values of U1 you will obtain is, I will just give you the final value, 1.9998, 2.9999, 2.9999, 4.00, and the maximum error here in this case will be 0.0003. So up to 3 decimal places the error value is now 0. So you have to continue until up to 3 decimal places the error value, the maximum error values are 0. Okay, so the maximum values, the maximum error for U1, U2, U3 is eventually reduced to 0.00 up to 3 decimal places after 8 iterations. So please take this as a kind of your exercise, because if I have to do all the calculations again, it will take a long time. So please fill up all these remaining boxes. So okay, I will stop for now. I will just take a few minutes break because I need water and other things. Then if you are free, we can start class again at 11:30. But in the meantime, before, sorry, class again at 12:30. So from 12:30 to I think within 30 minutes I can finish after that. So in the meantime, please finish up these calculations. So it is going to be like a kind of classroom exercise. Please finish up these boxes. Calculate the third iteration, fourth iteration, fifth, sixth, and seventh. Fill up all these boxes. Okay, so I will terminate now. We will resume our class at 12:30. Just one more class, and then I can finish this partial differential equations. Yeah, please finish up this.